Math. It's a really old and amazing subject. It's super important for our world and helps power cool things like computers and smartphones. Throughout history, there have been many brilliant mathematicians. These incredible people used their smarts and worked really hard to help math grow. Because of them, we have the knowledge we have today. This video will teach you about 10 of the greatest mathematicians ever. Their work changed how we understand math and even impacts how things like artificial intelligence work today. We're going to learn about Euclid, the father of geometry, Al-Khwarizmi, a pioneer in algebra and algorithms, Archimedes, a genius in geometry and physics, Pierre de Fermat, a founder of number theory, Isaac Newton, the inventor of calculus and the father of classical mechanics, Carl Friedrich Gauss, a key figure in modern mathematics, Leonhard Euler, a multi-talented mathematical genius, John von Neumann, a founder of computer science and game theory, David Hilbert, a modernizer of mathematics, and Chen Jingrun, who made breakthroughs in the study of Goldbach's conjecture. These mathematicians didn't just change math, they helped create modern science, engineering, computer science, and even artificial intelligence. We're going to learn about their lives, their biggest achievements, and how their work affects us even today. We'll even see how their discoveries are used in AI technology. Get ready to see how these amazing mathematicians changed the world. Our first mathematician is Euclid, who lived around 300 BC. Euclid was born in Alexandria, Egypt, which was part of ancient Greece. He's one of the most famous mathematicians ever. We don't know everything about his life, but we know his work is still super important today. Old books tell us that Euclid lived during the time of Ptolemy I, a ruler around 323 to 283 BC. Back then, Alexandria was like the coolest place to be if you loved to learn. They had the biggest library in the world, and people who loved knowledge came from everywhere to study. Euclid was one of them. Even though we don't know much about his childhood, we think he must have gone to really good schools. He probably learned about philosophy and math from the followers of Plato, a famous philosopher. Plato's people thought math was super important, like a secret code to understanding the universe. This idea probably made Euclid want to study math too. In Alexandria, Euclid wasn't just a student, he became a teacher. Some of his students became really important mathematicians and scientists themselves. People said Euclid was a tough teacher, but he made you think really hard and learn a lot. He wanted his students to understand why math worked, not just memorize the answers. Euclid loved geometry, but he was interested in other things too, like numbers, ratios, shapes in space, light, and even music. His work shows how much ancient Greek mathematicians loved learning and exploring. Euclid's work in Alexandria made him famous, and it also helped make ancient Greece really good at math. We might not know every detail about Euclid's life, but we know he was one of the most important mathematicians ever. His work helped create the math we use today, especially in geometry. Euclid's most famous work is his book called Elements. It's not just a math book, it's one of the most important science books ever written. Elements has 13 parts and talks about almost everything people knew about geometry back then, like shapes on flat surfaces, numbers, ratios, shapes in space, and even some really tricky math ideas. People used this book to learn for over 2,000 years, making it a super important textbook. Elements is famous for being super organized and logical. Euclid starts with 5 simple rules called axioms. These axioms are like things everyone can agree are true. Then he uses those rules to figure out all sorts of geometry facts, step by step. This way of using axioms changed how people thought about math. It helped geometry grow and gave all mathematicians a way to make sure their work made sense. Here are Euclid's 5 axioms. 1. You can draw a straight line between any 2 points. 2. You can make a line longer and longer forever. 3. You can draw a perfect circle around any point, any size you want. 4. All right angles are the same. 5. If you have 2 lines and another line crosses them, and the angles on one side add up to less than 2 right angles, then those 2 lines will eventually cross on that side. That 5th axiom about parallel lines caused a lot of discussion among mathematicians. They tried to prove it using the other axioms, but couldn't. This actually led to new types of geometry, which was really cool. The first 6 parts of Elements are about flat shapes like lines, angles, triangles, squares, and circles. Parts 7 through 10 are about numbers and ratios. Part 9 even has a famous proof that there are infinitely many prime numbers. The last 3 parts are about shapes in space, especially 3D shapes. This part of Elements was important for math that came much later. Euclid didn't just teach us geometry facts, he taught us how to think about math in a logical way. His method of using axioms is still how mathematicians work today, and it's influenced scientists and philosophers too. Euclid's book Elements was a huge deal. People all over ancient Greece and Rome read it, and it was even important in the Islamic world and during the European Renaissance. In ancient Rome, smart people had to read Elements, and it helped Roman architects and builders design amazing structures. Later, in the Islamic Golden Age, Arabic scholars translated Elements and even added their own ideas. This helped math grow even more and was important when Europe started focusing on learning again during the Renaissance. During the Renaissance, Europeans rediscovered ancient Greek knowledge, and Elements became super popular again. It wasn't just for scientists, it was the book for learning math. When the printing press was invented, Elements was one of the first books printed, so everyone could learn Euclid's ideas. Even in the 1800s, people still learned geometry from Euclid. Amazing mathematicians like Gauss, Riemann, and Bolzano studied Euclid's work, and it helped them come up with new types of geometry that were different from what Euclid imagined. This was a huge deal for math, and even helped Einstein develop his theories about gravity. Euclid's influence goes beyond just math. His logical way of thinking is used in philosophy, physics, engineering, and even computer science. For example, the philosopher Immanuel Kant talked about how Euclid's geometry relates to how our brains understand the world. In physics, Euclid's ideas were super important for a long time. Remember how geometry is about shapes and space? Well, AI uses geometry all the time, especially for things like computer vision, image processing, 3D modeling, and even telling robots how to move around. Computer vision helps computers see like we do. Euclid's geometry helps computers understand pictures and videos. Think about it, shapes, sizes, where things are. That's all geometry. This helps computers recognize objects, understand what's happening in a scene, and even track moving objects. Image processing is how computers change and improve images. Euclid's geometry helps with rotating, resizing, and moving images around. This is used for things like making photos look better or combining images. 3D modeling is how computers create those cool 3D worlds you see in movies and video games. Euclid's geometry helps computers understand how 3D shapes work, so they can create realistic-looking objects and environments. Robots use geometry to navigate too. They need to understand their surroundings and avoid bumping into things, and Euclid's geometry helps them figure out distances, directions, and paths. It's like their secret code for moving around. Euclid's way of using logic and axioms is also important for how AI systems think. AI needs to make decisions based on rules, just like in geometry. This helps make sure AI systems are reliable and make sense. Our second mathematician is Al-Khwarizmi, who lived around 780 to 850 AD. Al-Khwarizmi's full name is Muhammad ibn Musa al-Khwarizmi, and he was born in Persia, which is now called Uzbekistan. He was a famous mathematician, astronomer, and geographer, and is considered one of the most important thinkers from the Islamic Golden Age. His work wasn't just important for math, it helped Europe rediscover its love for learning during the Renaissance. We don't know everything about Al-Khwarizmi's childhood, but we know he must have had a good education in Baghdad, which was like the coolest city for knowledge back then. He probably studied and worked at the House of Wisdom, a famous place where smart people came together to share ideas. Al-Khwarizmi was interested in all sorts of things like math, astronomy, geography, and history. His work in math was super important, especially his ideas about algebra, algorithms, and the number system we use today. His books were read all over the Arab world and eventually translated into European languages, which changed how Europeans thought about math. Al-Khwarizmi's most famous work is a book about algebra called The Compendious Book on Calculation by Completion and Balancing. This book is like the Bible of algebra. In fact, the word algebra comes from the title of his book. This book explained how to solve equations, which are like math sentences, and it helped make algebra its own type of math. In his book, Al-Khwarizmi created the rules for solving equations step by step and showed how to use those rules to solve real-world problems, like dividing land or figuring out how much money people should inherit. He even explained how to solve those tricky quadratic equations, which involve squares and stuff. His work gave future mathematicians the tools to do even more amazing things with algebra. Al-Khwarizmi also helped us understand algorithms, which are like step-by-step instructions for solving problems. The word algorithm comes from his name. He wrote a book explaining how to use the number system we use today, with the digits 0 through 9. This made math so much easier and helped create the computers we use today. Al-Khwarizmi was good at astronomy and geography too. He made better star charts and wrote books about the stars and about the Earth. His book, The Book of the Description of the Earth, was like a map of the world back then and helped people understand geography better. Al-Khwarizmi's books were like bestsellers. People all over the Arab world and Europe read them, and they had a huge impact on mathematicians who came after him. His work in algebra and algorithms was especially important for the European Renaissance. In the Arab world, mathematicians loved Al-Khwarizmi's ideas. Scholars like Al-Khwarizmi and Al-Hassar used his work to explore even more complex math problems. It was like they were building on what he started. Al-Khwarizmi's books made their way to Europe through translations. In the 12th century, European mathematicians started reading his work and realized how important it was. His book on algebra was translated into Latin, the language of scholars, and became a textbook in European universities. Even famous European mathematicians like Fibonacci were inspired by Al-Khwarizmi's work. Al-Khwarizmi didn't just change math, he changed other subjects too. Algebra became a useful tool for physics, engineering, and economics, and his ideas about algorithms helped create the computers we use today. So, how are Al-Khwarizmi's ideas used in AI? Well, remember how he was the king of algebra and algorithms? Those are super important for AI. In computer science, algorithms are like the brains of AI. Almost every AI system uses algorithms to understand information and do tasks. Al-Khwarizmi's ideas about algorithms are used for everything from organizing data to those super complex algorithms used in machine learning. AI systems use algorithms to handle tons of information, find patterns, make predictions, and even make decisions. Some examples include algorithms used in deep learning, genetic algorithms, and even those used to solve optimization problems. Machine learning is how computers learn without being explicitly programmed. Algebra is super important for creating the math models that make machine learning work. Al-Khwarizmi's work helped us understand linear algebra, which uses matrices and vectors to solve problems. These ideas are used all the time in neural networks, support vector machines, and other machine learning algorithms. Natural language processing is how computers understand human language. AI systems use math to analyze text, and Al-Khwarizmi's work helped make that possible. They use algebra and algorithms to do things like text classification, sentiment analysis, figuring out if someone's happy or sad based on what they write, and even machine translation, like Google Translate. In computer science, we care about how efficient algorithms are. We want them to solve problems quickly. Al-Khwarizmi's ideas are used to solve really complex problems, like those found in image recognition, natural language processing, and recommendation systems, like how Netflix knows what movies you might like. Al-Khwarizmi's work in math and algorithms didn't just lay the groundwork for AI, it helped AI become useful in so many different fields. His ideas are still important today and will continue to shape technology in the future. Our third mathematician is Archimedes, who lived around 287 to 212 BC. Archimedes was born in Syracuse, a Greek city. He was a brilliant mathematician, physicist, engineer, and inventor. He wasn't just good at math, he loved figuring out how the world worked. Even though we don't know everything about his life, his work has inspired scientists and engineers for centuries. Archimedes grew up in a family that loved science. We think his dad, Phidias, was an astronomer. Maybe that's what sparked Archimedes' interest in science. As a young man, Archimedes went to Alexandria to study, just like Euclid did. Alexandria was the place to be if you loved learning. He might have even learned from Euclid's students. This experience definitely shaped how he thought about math and science. Archimedes loved studying shapes, forces, fluids, and building cool stuff. When he went back to Syracuse, he continued his research and even helped the king by designing weapons and defenses for the city. His inventions weren't just ideas, they actually worked. Archimedes was amazing. He made important discoveries in lots of areas, from shapes to forces to fluids to building things. Here are some of his biggest achievements. Geometry. Archimedes loved shapes. He figured out how to calculate the area and volume of curved shapes like circles and spheres. He even came up with a special spiral shape called the Archimedean spiral. He was especially interested in parabolas, hyperbolas, and ellipses, which are all types of curves. He also discovered a really important principle about buoyancy. He figured out that if you put something in water, the water pushes up on it with a force equal to the weight of the water the object pushes aside. This is why boats float. This principle is still super important in physics and engineering. Mechanics and engineering. Archimedes discovered the lever. He realized that a lever could be used to lift heavy objects with less force, depending on where you push or pull. He even said, "Give me a place to stand, and I shall move the earth." He also invented the Archimedes screw, which is like a big spiral screw that can lift water. This invention is still used today. Archimedes also designed all sorts of cool weapons and defenses for his city, like catapults and walls that could protect the city from invaders. Mathematical analysis. Archimedes was way ahead of his time. He came up with a method called the method of exhaustion to calculate the area of curved shapes. This method was like a sneak peek into calculus, which wouldn't be invented for another 2,000 years. He used this method to figure out the area of a circle and the volume of a sphere, which were big discoveries in math. Archimedes' work was so important that he's called the father of science. His discoveries in geometry were a big deal for mathematicians who came after him, especially those who developed calculus, like Newton and Leibniz. His work on levers and buoyancy became super important in physics and engineering. His inventions and designs inspired people for centuries. During the Middle Ages, Arabic scholars translated Archimedes' work, so people in the Islamic world could learn from him too. Later, during the Renaissance, European scholars rediscovered his work, and it was like finding treasure. They used his ideas to make new discoveries in science and math. Famous scientists like Galileo and Newton were huge fans of Archimedes. They used his work as inspiration for their own research, which led to even more amazing discoveries. Believe it or not, Archimedes' work is still used in AI today. His ideas about shapes, forces, and fluids are helpful for things like computer simulations, making things work better, and even controlling robots. Here are some examples. Geometry and computer graphics. Remember how Archimedes loved shapes? Well, his work is super important for computer graphics, which is how computers create those cool 3D images and animations you see in movies and video games. Archimedes' method of exhaustion is even used to make those images look more realistic. Physics, simulations, and mechanics. Archimedes' ideas about levers and buoyancy are used in physics simulations, which are like virtual experiments. These simulations help us understand how things move and interact in the real world, and they're used in robotics, video games, and even virtual reality. Machine learning and optimization. Remember how Archimedes used the method of exhaustion to solve problems? Well, similar ideas are used in machine learning to find the best solutions to problems. This helps AI systems learn and make better predictions. Computational fluid dynamics. Archimedes' work on fluids is still relevant today in a field called computational fluid dynamics. This field uses computers to simulate how fluids flow, which is helpful for designing airplanes, cars, and even predicting the weather. Archimedes wasn't just a brilliant mind from the past. His work is still shaping the future, especially in the world of AI. Our fourth mathematician is Pierre de Fermat, who lived from 1607 to 1665. Pierre de Fermat was born in France and became one of the greatest mathematicians ever. He was amazing at math, but he was also a successful lawyer and government official. Fermat helped create number theory, probability theory, analytic geometry, and even calculus. His work is still studied by mathematicians today. Fermat's family was well off. His dad was a leather merchant and his mum came from a family of lawyers. Fermat got a great education and went to a university in Toulouse to study law. He became a lawyer but loved math in his spare time. He would write letters to other mathematicians, sharing his amazing ideas. Fermat was interested in all sorts of math problems, like those dealing with numbers, chances, shapes, and even how things change. He made groundbreaking discoveries, even though he shared a lot of his work through letters and notes. Fermat is sometimes called the father of number theory because he was a genius at solving problems with numbers. Here are some of his most famous contributions. Fermat's last theorem. This is probably Fermat's most famous puzzle. He wrote it down in the margin of a book, saying he had a proof, but there wasn't enough space to write it down. This little note puzzled mathematicians for over 350 years. Fermat's last theorem says that you can't find three whole numbers that fit into the equation, a circumflex, n plus b circumflex, an equal sign c circumflex, n if n is bigger than 2. It seems simple, but it was incredibly difficult to prove. Finally, in 1994, a mathematician named Andrew Wiles solved the puzzle. Fermat's little theorem. This theorem is another one of Fermat's important discoveries about numbers. It helps us understand how prime numbers work, and it's even used in cryptography, which is how we keep information secret online. Analytic geometry. Fermat figured out a way to connect algebra and geometry, which was a big deal. He realized that you could use equations to describe shapes and solve geometry problems. This discovery helped pave the way for calculus. Probability theory. Fermat and his friend Blaise Pascal helped create probability theory, which is all about understanding the chances of something happening. They started by thinking about gambling problems, but their work is now used in statistics, economics, and even computer science. Calculus. Fermat also made important contributions to calculus, even though he didn't develop it as fully as Newton and Leibniz did later on. He had ideas about how to find the slopes of curves and how to find the highest and lowest points on curves, which are important concepts in calculus. Fermat's work was like a gift that kept on giving. His ideas about numbers, shapes, chances, and calculus had a huge impact on math and other fields. His work in number theory inspired mathematicians like Euler, Gauss, and Riemann, who made their own amazing discoveries. His work in analytic geometry helped create a whole new way of thinking about math, connecting algebra and geometry. This was a big deal for math, and his work with Pascal on probability theory is still used today in fields like finance, insurance, and medicine. Even though he didn't fully develop calculus, his ideas helped inspire Newton and Leibniz, who created this powerful tool that's used in physics, engineering, economics, and so many other fields. Fermat's mathematical ideas are still used in AI today, especially in cryptography, machine learning, computer vision, and even self-driving cars. Number theory and cryptography. Remember Fermat's little theorem. It's used to keep our information safe online. Many encryption algorithms, which are like secret codes, rely on Fermat's work to make sure that only authorized people can access our data. Probability theory and machine learning. Fermat's work on probability is super important for machine learning. Probability helps computers make predictions and decisions based on data. For example, it's used in speech recognition, natural language processing, and those recommendation systems that suggest movies you might like. Analytic geometry and computer vision. Fermat's work on connecting algebra and geometry is used in computer vision, which helps computers see and understand images. It helps computers recognize objects, match images, and even create 3D models from images. Optimization in AI. Fermat's ideas about finding the best solutions are used in AI all the time. When we train AI models, we need to find the best settings so that the model can learn effectively. Fermat's work helps us develop algorithms to do this. Tangent lines and self-driving cars. Believe it or not, Fermat's ideas about tangent lines, which are lines that touch a curve at a single point, are used in self-driving cars. These cars need to calculate their trajectories, or paths, and Fermat's work helps them do this accurately and safely. Fermat's mathematical legacy continues to shape the world we live in, especially in the exciting field of AI.
Isaac Newton, born in Woolsthorpe, Lincolnshire, England in 1643, is one of the greatest mathematicians, physicists, and astronomers in history. He not only achieved outstanding achievements in mathematics, but also made revolutionary contributions in many fields such as physics, astronomy, and philosophy. Newton is one of the inventors of calculus. His research laid the foundation of modern science and greatly influenced the subsequent development of science. When Newton was born, his father had died and he was raised by his mother and grandmother in his childhood. During his school years, Newton showed extraordinary intelligence and a strong interest in natural sciences. In 1661, Newton entered Trinity College, Cambridge University, and initially studied classical courses, but soon he developed a strong interest in mathematics and physics. Influenced by Descartes, Galileo, and Kepler, Newton began to study mathematics, astronomy, and mechanics in depth, and spent most of his career at Cambridge University. Newton's research fields are wide-ranging, including mathematics, optics, astronomy, mechanics, and natural philosophy. His work not only made important breakthroughs in theory, but also had a profound impact in practice. Newton is known as the father of modern science, and his ideas and methods are of epoch-making significance in the history of science. Newton's greatest contribution to mathematics is the calculus he invented almost at the same time as Leibniz. This mathematical tool greatly expanded the scope of mathematical analysis, making it possible to deal with the calculation of rates of change and cumulative quantities. Calculus has become a key tool for solving complex problems in fields such as physics, engineering, and economics. The invention of calculus. Newton invented calculus when studying the motion of planets and the acceleration of objects. He proposed the concepts of differentials and integrals. Differentials are used to solve rate problems, and integrals are used to solve area and volume problems. Newton's calculus method is called the fluxion method. By analyzing the trajectory of an object's motion, Newton was able to derive the velocity and acceleration of the object at different points in time. The invention of calculus is a major breakthrough in the history of science, and it provides a powerful mathematical tool for dealing with complex physical problems. Newton-Leibniz controversy. Although Newton and Leibniz invented calculus almost at the same time, the priority dispute between the two lasted for many years. There are some conceptual differences between Newton's fluxion method and Leibniz's differential method, but they are essentially the basis of calculus. Regardless of the priority, the invention of calculus has a profound impact on the development of mathematics and promoted the progress of the scientific revolution. The foundation of classical mechanics. Newton's most well-known contribution is his research in the field of mechanics. His mathematical principles of natural philosophy, Philosophiae Naturalis Principia Mathematica, is regarded as one of the most important works in the history of science. In this book, Newton systematically expounded the three laws of motion and the law of universal gravitation, laying the foundation for classical mechanics. The first law, law of inertia, an object will remain at rest or in a state of uniform rectilinear motion in the absence of an external force. The second law, law of acceleration. The acceleration of an object is proportional to the force and inversely proportional to the mass of the object. The third law, law of action-reaction. For every action, there is an equal and opposite reaction. These laws not only explain the movement of objects on Earth, but also reveal the gravitational forces between celestial bodies. Newton's law of universal gravitation states that the gravitational force between two objects is proportional to their masses and inversely proportional to the square of the distance between them. This discovery provides a theoretical basis for understanding planetary motion, tidal phenomena, and the structure of the universe. Optical research. Newton's research in the field of optics is equally outstanding. Through the prism experiment, he discovered that white light is composed of multiple colors of light, a discovery that changed people's understanding of light. Newton also proposed the particle theory of light, believing that light is composed of tiny particles, a view that was later confirmed by the development of quantum mechanics. Newton's optical research promoted the development of telescopes and greatly promoted the progress of astronomy. Newton's research has had a wide and far-reaching impact on later generations. His classical mechanics system has become the basis of scientific research and has influenced scientific development for centuries. In the field of physics, Newton's laws of motion and law of universal gravitation became the cornerstone of classical mechanics, guided subsequent physics research, and provided theoretical support for disciplines such as engineering, astronomy, and mechanics. Newton's invention of calculus opened up new research areas for modern mathematics. Calculus became a core tool in mathematical analysis, physics, engineering, and economics, used to solve problems such as rate of change, optimization, and cumulative quantities. The application range of calculus is very wide, from describing planetary motion to predicting economic trends to optimizing engineering design. Calculus is everywhere. Newton's optical research had a profound impact on later physicists. His particle theory of light paved the way for the birth of quantum mechanics, and his research on the nature of light also provided the basis for the development of modern optics and photonics. Newton's telescope design was continuously improved and became an important tool for astronomical research. Newton's ideas and methods influenced the entire scientific revolution and laid the foundation for modern science. He emphasized the importance of experiment and observation and introduced mathematical methods into the study of natural philosophy, a methodology widely adopted by later scientists. Newton's work not only made great achievements in science, but also had an important impact on the formation of positivism in philosophy. Newton's mathematical and physical research has had a profound impact on the development of modern AI technology. Here are some specific applications. Calculus and machine learning. Calculus is an important tool for mathematical modeling in machine learning. Many machine learning algorithms rely on calculus to calculate the gradient of the model to optimize the model parameters. Gradient descent is a typical application of calculus in machine learning. It finds the optimal value of model parameters by calculating the gradient of the loss function. This process is widely used in machine learning models such as deep learning, neural network training, and support vector machines. Optimization and automatic control. Newton's calculus ideas have been widely used in optimization and automatic control. Optimization problems are core problems in AI and involve finding the best solution or strategy to maximize or minimize a certain objective function. Newton's differential method and extreme value theorem provide the basis for modern optimization algorithms, especially in complex multidimensional spaces, where optimization algorithms rely on accurate differential calculations to navigate the solution space. Physics simulation and computer graphics. Newton's classical mechanics is widely used in physics simulation and computer graphics. Physics simulation relies on Newton's laws of motion and the law of gravity to predict the movement and interaction of objects. In computer graphics, the movement and deformation of objects are often achieved through physical simulation to create realistic visual effects. These techniques are widely used in game development, movie special effects, virtual reality, and other fields. Robot control and path planning. Newton's laws of motion also have important applications in robot control and path planning. Robot systems rely on classical mechanics to calculate motion trajectories and control torques to achieve precise operation. Newton's mechanics theory provides a mathematical foundation for the design and control of robotic systems, allowing robots to operate safely and efficiently in complex environments. Optics and computer vision. Newton's optical research has had a profound impact on computer vision and image processing. Computer vision systems rely on optical principles to understand and process images, especially in color analysis and illumination models, where Newton's optical theory provides a foundation. Image segmentation, edge detection, and object recognition algorithms in computer vision all rely on models of light propagation and reflection, which are derived from Newton's optical research. Newton's mathematical and physical research not only laid the foundation for modern science, but also promoted the development of modern AI technology through fields such as calculus, classical mechanics, and optics. From machine learning to physical simulation to computer vision, Newton's ideas still play an important role in today's technological world. Carl Friedrich Gauss, born in Brunswick, Germany in 1777, is one of the greatest mathematicians in history. He is known as the Prince of Mathematics and has made outstanding contributions in many fields such as number theory, algebra, geometry, statistics, astronomy, and physics. Gauss's research laid the foundation for modern mathematics and greatly promoted the progress of science. Gauss was born into a poor family. His father was a bricklayer and his mother was a farmer. Despite the difficult economic conditions of his family, Gauss showed extraordinary mathematical talent since he was a child. According to legend, Gauss was able to correct his father's arithmetic errors at the age of 3, and at the age of 10, he solved a complex mathematical problem by a fast summation method, an event that quickly attracted the attention of mathematicians. With the Duke's sponsorship, Gauss was able to study at the Karolinska Institute in Brunswick and then at the University of Göttingen to study mathematics. His research during college covered number theory, geometry, and analysis, showing his extensive knowledge and innovative ability in mathematics. Gauss's mentor had high hopes for him and provided him with the opportunity to continue his studies. Gauss devoted his life to mathematical and scientific research. He not only proposed many important mathematical theories, but also applied these theories to fields such as physics and astronomy. His research methods were rigorous and creative, which greatly promoted the development of mathematics and science. Gauss's contributions to mathematics and science were extensive and far-reaching, and he deserved to be called the Prince of Mathematics. Here are some of his most important contributions. Number theory. Gauss's research on number theory is a classic, and his book Disquisitiones Arithmetica is considered to be the foundation of number theory. The book covers the core concepts of number theory such as prime numbers, congruences, and quadratic reciprocity laws, and proposes many new theorems. In this book, Gauss systematically developed the theory of modular arithmetic and proved the quadratic reciprocity law, which is of epoch-making significance in number theory. Algebra. Gauss's contribution to algebra is equally outstanding. He proved the fundamental theorem of algebra, that is, every non-constant univariate polynomial has at least one root in the complex field. This theorem is the cornerstone of algebra and has a profound impact on the solution of polynomial equations. Gauss also introduced the concept of the complex plane to represent complex numbers, which greatly expanded the horizon of mathematics. Geometry. Gauss proposed the concept of Gaussian curvature in geometry and laid the foundation for differential geometry. Gaussian curvature is used to describe the curvature of a surface and is an important tool in modern geometry. He also studied the possibility of non-Euclidean geometry. Although he did not publish this research publicly, his work paved the way for the later non-Euclidean geometry theories of Riemann and Lobachevsky. Statistics and error theory. Gauss's contribution to statistics is mainly reflected in the study of error theory and normal distribution. Normal distribution, also known as Gaussian distribution, is a basic concept in probability theory and statistics, used to describe the central tendency and distribution of data. The least squares method proposed by Gauss is a standard method for data fitting and is widely used in fields such as astronomy, physics, and economics. Astronomy and physics. Gauss not only made outstanding achievements in mathematics, but also applied these achievements to astronomy and physics. He successfully predicted the orbit of Ceres and accurately calculated the motion of the planet through the least squares method. This achievement made him famous in the astronomical community. Gauss also made important contributions to magnetism and proposed Gauss's theorem to describe the distribution of electric and magnetic fields. This theory is of great significance in electromagnetism. Gauss's research has had a wide and profound impact on the development of mathematics and science in later generations. First, his work in number theory laid the foundation for modern number theory. Gauss's research on arithmetic not only influenced later mathematicians such as Dirichlet, Riemann, and Hermite, but also inspired many new research directions in number theory. such as algebraic number theory and analytic number theory. In algebra, Gauss's fundamental theorem of algebra and complex number theory provided the cornerstone for the development of modern algebra. His concept of the complex plane enabled mathematicians to better understand and manipulate complex numbers, laying the foundation for the development of complex analysis. Gauss's algebraic ideas influenced many later mathematicians, such as Galois, Abel, and Jacobi, who further developed algebraic theory in fields such as polynomial equations and group theory. Gauss's contribution to geometry laid the foundation for the formation of differential geometry. His concept of Gaussian curvature is not only of great significance in mathematics, but is also widely used in physics, astronomy, and engineering. Gauss's geometric ideas influenced mathematicians such as Riemann, Lobachevsky, and Klein, whose research in non-Euclidean geometry and topology greatly expanded the territory of mathematics. Gauss's contributions to statistics and error theory laid the foundation for modern statistics. Normal distribution and the least squares method have become important tools in fields such as data analysis, economics, physics, and biology. Gauss's statistical ideas influenced later mathematicians and statisticians such as Fisher, Small, and Kelly, whose research in probability theory and statistics greatly promoted the development of these fields. In astronomy and physics, Gauss's work not only promoted the progress of astronomy, but also provided a theoretical basis for the development of electromagnetism. His Gaussian theorem became one of the basic theorems of electromagnetism and was widely used in the calculation and analysis of electromagnetic fields. Gauss's scientific ideas had a profound impact on later physicists, such as Maxwell, Hertz, and Einstein. Gauss's mathematical and scientific research has a wide range of applications in modern AI technology, especially in the fields of number theory, statistics, geometry, and physics. Here are some specific applications. Normal distribution and machine learning. Gaussian normal distribution is an important tool for probability models in machine learning. Many machine learning algorithms rely on normal distribution to model the distribution of data and make predictions and classifications. For example, algorithms such as Bayesian classifiers, linear discriminant analysis, and Gaussian mixture models all use normal distribution to represent the probability distribution of data. These algorithms are widely used in fields such as image recognition, natural language processing, and recommendation systems. Number theory and cryptography. Gauss's research in number theory has had an important impact on modern cryptography. Number theory concepts such as modular arithmetic and quadratic reciprocity law are widely used in encryption algorithms, such as the RSA encryption algorithm and elliptic curve encryption algorithm. Gauss's number theory ideas provide a mathematical basis for the development of secure encryption systems to ensure the security of data during transmission, geometry, and computer vision. Gauss's contributions to geometry have had a profound impact on modern computer vision. Gaussian curvature is used to describe the shape and structure of surfaces and is an important tool in three-dimensional reconstruction and image processing.
Our eighth mathematician is John von Neumann. John von Neumann, 1903–1957. John von Neumann, John von Neumann, was born in Budapest, Hungary in 1903. He's considered one of the most brilliant mathematicians of the 20th century. Not only did he achieve amazing things in math, but he also made groundbreaking contributions to physics, computer science, economics, and statistics. Von Neumann is known as the father of modern computer science, and his influence on math and science is huge. Von Neumann was born into a wealthy Jewish family. His father was a banker and his mother was a homemaker. He showed incredible talent in math from a very young age. When he was only 6, he could do complex calculations in his head and could even recite an entire phone book from memory. While studying in Budapest, he received a top-notch European education in math, especially at the University of Budapest and ETH Zurich. This made him one of the most promising young mathematicians of his time. In 1926, von Neumann earned a doctorate in chemical engineering, but he quickly switched to math research. He completed groundbreaking work on quantum mechanics at the University of Göttingen. After that, he taught at Princeton University and the Institute for Advanced Study, becoming one of its founding professors. Von Neumann's research covered math, physics, computer science, economics, and statistics. His work in these areas laid the foundation for modern science and technology. Von Neumann's contributions to mathematics are vast and far-reaching, spanning from pure mathematics to applied mathematics. Here are some of his most important contributions. Quantum mechanics and von Neumann. Algebra. Von Neumann made revolutionary contributions to the mathematical foundations of quantum mechanics. He developed the theory of Hilbert spaces and proposed von Neumann algebra, also known as operator algebra, an algebraic structure used to describe the theory of operators in quantum mechanics. Von Neumann algebra is not only significant in quantum mechanics, but also widely used in statistical mechanics and information theory. Game theory and economics. Von Neumann, in collaboration with Oscar Morgenstern, pioneered the new mathematical field of game theory. Game theory studies the interactions between decision-makers in competitive environments and has become an important tool in modern economics, political science, and social science. Von Neumann proposed the concepts of zero-sum games and mixed-strategy Nash equilibrium in game theory, which are widely used in market analysis, strategic planning, and artificial intelligence. Computer science and von Neumann. Architecture. Von Neumann is one of the founders of modern computer science. He proposed the von Neumann architecture, which forms the basis of most modern computer systems. The core idea of the von Neumann architecture is to unify the computer's memory, controller, arithmetic logic unit, and input/output devices into one system, and use stored programs to control the computation process. This architecture greatly simplified computer design and promoted the popularization and development of computers. Numerical analysis and numerical analysis. Von Neumann also made important contributions to numerical analysis and computational methods. He proposed numerical methods for solving differential equations and integral equations, which are widely used in scientific computing, engineering simulation, and computational physics. Von Neumann also proposed a binary-based floating-point representation method, which has become the standard for modern computer calculations. Stochastic processes and Markov chains. Von Neumann's work on stochastic processes and Markov chain theory greatly advanced these fields. He proposed the von Neumann random number generation method, an algorithm for generating pseudo-random numbers, widely used in simulation, statistics, and cryptography. Von Neumann's stochastic process theory is widely used in statistical physics, financial mathematics, and computational biology. Von Neumann's research has had a wide and profound impact on the development of mathematics and science for future generations. First, his work in quantum mechanics laid the mathematical foundation for modern physics. Von Neumann algebra became a fundamental tool in quantum mechanics, used to describe quantum states and operations. Von Neumann's ideas about quantum mechanics influenced later physicists like Feynman, Weinberg, and Hawking, who further developed these theories in quantum field theory and quantum gravity. In game theory and economics, von Neumann's work opened up a whole new field of study. Game theory has not only become an important tool in modern economics, but has also been widely used in computer science, social sciences, and biology. Von Neumann's ideas about game theory influenced later economists like Nash, Arrow, and Sen, who further developed these theories in game theory, social choice theory, and welfare economics. Von Neumann's contributions to computer science laid the foundation for modern computers. The von Neumann architecture became the design standard for most modern computer systems, widely used in personal computers, servers, supercomputers, and embedded systems. Von Neumann's ideas about computer science influenced later computer scientists like Turing, Shannon, and von Neumann himself, who further developed these theories in computation theory, information theory, and artificial intelligence. Von Neumann's theories on numerical analysis and stochastic processes are widely used in modern scientific computing and engineering simulation. Von Neumann's numerical methods and random number generation algorithms are used to solve complex scientific problems, such as climate modeling, nuclear reaction simulation, and financial risk analysis. Von Neumann's ideas about numerical analysis influenced later mathematicians and computational scientists, like von Karman, one of von Neumann's students, who further developed these theories in computational fluid dynamics and numerical optimization. Von Neumann's mathematical and scientific research has wide applications in modern AI technology, especially in game theory, computer science, numerical analysis, and stochastic processes. Here are some specific applications: game theory and strategic planning. Von Neumann's contributions to game theory have profoundly impacted strategic planning and decision support in modern AI. Game theory is used to analyze and optimize decision-making processes in multi-agent systems, widely used in autonomous driving, financial trading, supply chain management, and military strategy. Von Neumann's ideas about game theory provide the basis for developing intelligent strategies and optimization algorithms, enabling AI systems to make effective decisions in complex environments. Computer architecture and deep learning. Von Neumann's contributions to computer architecture have significantly impacted modern deep learning systems. The von Neumann architecture is widely used in the training and inference processes of deep learning models, especially in computationally demanding deep neural networks. Von Neumann's ideas about computer architecture provide the basis for developing efficient deep learning systems, enabling AI systems to process large-scale data and perform complex tasks. Numerical analysis and optimization algorithms. Von Neumann's contributions to numerical analysis have profoundly impacted modern optimization algorithms. Numerical analysis is used to solve optimization problems in machine learning, such as gradient descent and Newton's method, widely used to train neural networks and adjust model parameters. Von Neumann's ideas about numerical analysis provide the basis for developing efficient optimization algorithms, enabling AI systems to find optimal solutions in complex, high-dimensional spaces. Stochastic processes and generative adversarial networks. Von Neumann's research on stochastic processes has significantly impacted modern generative adversarial networks, GANs. Stochastic processes are used to model and generate pseudo-random numbers, which GANs use to generate realistic images, sounds, and text. Von Neumann's ideas about stochastic processes provide the basis for developing generative adversarial networks and other generative models, enabling AI systems to generate high-quality content in unsupervised learning environments. Markov chains and reinforcement learning. Von Neumann's contributions to Markov chain theory have profoundly impacted modern reinforcement learning. Reinforcement learning algorithms use Markov decision processes, MDPs, to model the interaction between agents and the environment, widely used in robot control, game AI, and autonomous driving. Von Neumann's ideas about Markov chains provide the mathematical foundation for developing reinforcement learning algorithms, enabling AI systems to learn and adapt in dynamic environments. Von Neumann's mathematical and scientific research not only laid the foundation for modern mathematics, but also promoted the development of modern AI technology through fields such as game theory, computer science, numerical analysis, and stochastic processes. From strategic planning to deep learning to generative adversarial networks and reinforcement learning, von Neumann's ideas continue to play an important role in today's technological world. Our ninth mathematician is David Hilbert. David Hilbert, 1862–1943. David Hilbert. David Hilbert was born in Königsberg, Germany in 1862. He's considered one of the greatest mathematicians in history. Not only did he achieve amazing things in math, but he also made significant contributions to physics, logic, and philosophy. Hilbert is known as the founder of modern mathematics, and his research significantly advanced the formalization and abstraction of mathematics. Hilbert was born into a family of scholars. His father was a judge, and his mother came from a wealthy academic family. At the University of Königsberg, Hilbert received the best mathematical education of the time, especially under the guidance of famous mathematicians Felix Klein and Hermann Minkowski. He demonstrated extraordinary mathematical talent. Hilbert's research during his university years covered geometry, number theory, and calculus of variations, demonstrating his broad knowledge and innovative ability in mathematics. After completing his studies, Hilbert joined the University of Göttingen as a faculty member and spent most of his career there. Under Hilbert's leadership, the University of Göttingen became one of the world's most important centres for mathematical research in the early 20th century. Hilbert's research covered almost all branches of mathematics. His work laid the foundation for modern mathematics and influenced the research directions of countless mathematicians who came after him. Hilbert's mathematical contributions are vast and far-reaching, spanning from geometry to mathematical logic. Here are some of his most important contributions: geometry and Hilbert's axiomatic system. Hilbert proposed Hilbert's axiomatic system in geometry, which is a systematization and formalization of Euclidean geometry. This axiomatic system makes geometry a rigorous mathematical system by precisely defining and axiomatizing the basic concepts in geometry, such as points, lines, planes, etc. Hilbert's research on geometry laid the foundation for modern geometry and influenced later mathematicians such as Bernstein, Vinogradov, and von Neumann, who further developed these theories in geometry and topology. Number theory and Hilbert's symbols. Hilbert's contributions to number theory are also significant. He proposed Hilbert symbols, a symbolic system for representing quadratic forms. Hilbert symbols have important applications in class field theory and modular form theory, and are widely used to study algebraic structures and Diophantine equations in number theory. Hilbert also proposed many conjectures about prime numbers, algebraic number theory, and modular forms, which have become important directions in number theory research. Mathematical logic and Hilbert's program. Hilbert's work in mathematical logic greatly promoted the development of this field. He proposed Hilbert's program, which aims to prove the consistency and completeness of mathematics by formalizing its foundations. The goal of Hilbert's program is to establish a rigorous axiomatic system to prove the correctness of mathematical propositions through formalized reasoning. Although this program failed to be fully realized due to Gödel's incompleteness theorems, Hilbert's formalization ideas have profoundly impacted mathematical logic and computer science. Infinity and calculus of variations. Hilbert's contributions to infinity theory and calculus of variations are also among his important achievements. He proposed Hilbert space, an abstract concept of infinite-dimensional vector space, which has become an important tool in modern analysis and quantum mechanics. Hilbert space is widely used in mathematical physics, quantum field theory, and functional analysis. Hilbert also proposed the Hilbert variational principle in calculus of variations, which is used to solve extremum problems and is widely used in physics and engineering. Mathematical foundations and Hilbert's problems. Hilbert's contributions to the study of mathematical foundations cannot be ignored. He proposed 23 famous Hilbert's problems in 1900, covering various branches of mathematics, including geometry, number theory, algebra, analysis, and mathematical logic. These problems became the main direction of mathematical research in the 20th century and greatly promoted the development of mathematics. Many Hilbert's problems were solved in the following decades, becoming important milestones in the history of mathematics. Hilbert's research has had a wide and profound impact on the development of mathematics and science for future generations. First, his work in geometry laid the foundation for modern geometry. Hilbert's axiomatic system provided a rigorous mathematical foundation for geometry and promoted the formalization and abstraction of geometry. Hilbert's geometric ideas influenced later mathematicians such as Bernstein, Vinogradov, and von Neumann, who further developed these theories in geometry and topology. In number theory, Hilbert's work greatly promoted the development of algebraic number theory. Hilbert's symbols and Hilbert's conjectures have become important tools and directions in number theory research, influencing later mathematicians such as Artin, Sheldon, and Langlands, who further developed these theories in class field theory, modular forms, and arithmetic geometry. Hilbert's ideas about number theory also promoted the development of cryptography, especially in public key cryptography and algebraic coding, where Hilbert's number theoretic methods are widely used. Hilbert's contributions to mathematical logic laid the foundation for modern logic and computer science. Although Hilbert's program was not fully realized, it promoted the formalization of mathematics and significantly impacted the development of mathematical logic. Hilbert's logical ideas influenced later logicians such as Gödel, Turing, and von Neumann, who further developed these theories in mathematical logic, computation theory, and artificial intelligence. Hilbert's work in infinity theory and calculus of variations laid the foundation for modern analysis and mathematical physics. Hilbert's space has become an important tool in quantum mechanics and functional analysis, and is widely used in mathematical physics, quantum field theory, and statistical mechanics. Hilbert's ideas about calculus of variations influenced later physicists such as Einstein, Dirac, and Feynman, who further developed these theories in relativity, quantum mechanics, and field theory. Hilbert's research on mathematical foundations provided an important direction for the development of mathematics in the 20th century. Hilbert's problems covered various branches of mathematics, promoting research in geometry, number theory, algebra, analysis, and mathematical logic. The solution of Hilbert's problems has greatly promoted the development of mathematics and stimulated the creativity of mathematicians, making mathematics a richer and more complex discipline. Hilbert's mathematical and scientific research has wide applications in modern AI technology, especially in mathematical logic, number theory, geometry, and optimization. Here are some specific applications. Mathematical logic and formal verification. Hilbert's contributions to mathematical logic have profoundly impacted formal verification and automated theorem proving in modern AI. Formal verification is used to verify the correctness of software and hardware systems, widely used in autonomous driving, aerospace, financial trading, and network security. Hilbert's formalization ideas provide the basis for developing formal verification tools and automated theorem-proving systems, enabling AI systems to ensure the reliability and security of their operations. Number theory and cryptography. Hilbert's research on number theory has significantly impacted modern cryptography. Hilbert's symbols and class field theory are widely used in cryptographic algorithms, especially in public key crypto systems. Hilbert's ideas about number theory provide the mathematical foundation for developing secure crypto systems, ensuring the security of data during transmission. Geometry and computer vision. Hilbert's contributions to geometry have profoundly impacted modern computer vision. Hilbert's axiomatic system provides a rigorous mathematical foundation for geometric modeling and image processing. Computer vision systems use geometric methods to understand and process images, especially in object recognition, image registration, and 3D reconstruction. Hilbert's geometric ideas provide the basis for developing efficient algorithms. Optimization and deep learning. Hilbert's work in calculus of variations has profoundly impacted modern optimization algorithms. Calculus of variations is used to solve optimization problems in deep learning, such as parameter tuning in machine learning and gradient descent in deep learning. Hilbert's ideas about calculus of variations provide the basis for developing efficient optimization algorithms, enabling AI systems to find optimal solutions in complex, high-dimensional spaces. Infinity theory and quantum computing. Hilbert's contributions to infinity theory have significantly impacted modern quantum computing. Hilbert's space is a fundamental tool in quantum mechanics and is widely used in quantum computing and quantum information processing. Hilbert's ideas about infinity theory provide the mathematical foundation for developing quantum algorithms and quantum computers, enabling AI systems to leverage the properties of quantum mechanics to handle complex computational tasks. Hilbert's mathematical and scientific research not only laid the foundation for modern mathematics, but also promoted the development of modern AI technology through fields such as mathematical logic, number theory, geometry, and optimization. From formal verification to deep learning to quantum computing and cryptography, Hilbert's ideas continue to play an important role in today's technological world. Our 10th mathematician is Chen Jingrun. Chen Jingrun, 1933–1996. Chen Jingrun was born in Fuzhou, Fujian Province, China, in 1933. He is one of the most outstanding mathematicians of the 20th century. He is best known for his remarkable achievements in number theory, especially his contributions to the Goldbach conjecture. Chen Jingrun's research significantly advanced modern number theory and earned international recognition for the Chinese mathematical community. Chen Jingrun was born into an ordinary family. His father was a primary school teacher, and his mother was a housewife. Chen Jingrun showed a strong interest in mathematics from an early age and demonstrated extraordinary mathematical talent during middle school. In 1950, Chen Jingrun was admitted to the Department of Mathematics at Xiamen University. There, he was instructed by famous mathematicians Chen Jingrun and Jiang Zehan, and showed great potential in number theory. After graduating from Xiamen University, Chen Jingrun entered the Institute of Mathematics of the Chinese Academy of Sciences, where he studied under Hua Luogeng and focused on number theory research. His work at the institute was tough, but he overcame various difficulties with great perseverance and made groundbreaking progress in the study of Goldbach's conjecture. Chen Jingrun's research results have attracted great attention in the Chinese mathematical community and have had a profound impact on the international mathematical community. Chen Jingrun's mathematical contributions are mainly concentrated in number theory, especially in the study of Goldbach's conjecture. Here are some of his most important contributions: Goldbach's conjecture and Chen's theorem. Chen Jingrun's most famous contribution is his breakthrough in the study of Goldbach's conjecture. Goldbach's conjecture is one of the most famous unsolved problems in number theory. It states that any even number greater than 2 can be expressed as the sum of two prime numbers. In a paper published in 1973, Chen Jingrun proved 1 + 2, that is, any sufficiently large even number can be expressed as the sum of a prime number and a number that is the product of at most two prime numbers. This result is called Chen's theorem, a major breakthrough in the study of Goldbach's conjecture, paving the way for the final solution to this problem. Prime number distribution and sieve methods. Chen Jingrun also made important contributions to prime number distribution and sieve methods. By improving and developing sieve methods, he solved some important problems in number theory, such as prime number distribution and congruences. Chen Jingrun's research on sieve methods provided new ideas and methods for many problems in number theory. Especially when solving problems related to prime numbers, sieve methods have become a powerful tool. Modular forms and analytic number theory. Chen Jingrun also made important contributions to modular forms and analytic number theory. He studied the application of modular forms in number theory, especially in analytic number theory. Chen Jingrun's research revealed a deep connection between modular forms and prime number distribution, providing important insights for later mathematicians' research in this field. Inequality problems in number theory. Chen Jingrun also achieved important results in the study of inequality problems in number theory. He proposed and proved some new inequalities that have important applications in the study of number theory. Especially when studying prime number distribution and congruence problems, Chen Jingrun's inequalities provided a new perspective for understanding complex structures in number theory. Chen Jingrun's research has had a wide and profound impact on the development of mathematics for future generations. First, his breakthrough in Goldbach's conjecture greatly promoted the study of number theory. Chen's theorem not only provided important progress towards the final solution of Goldbach's conjecture, but also inspired new research directions in the field of number theory. Chen Jingrun's work has become an important milestone in number theory research, influencing later mathematicians such as Zhang Yitang and Terence Tao, who further developed these theories in prime number theory and analytic number theory. In terms of prime number distribution and sieve methods, Chen Jingrun's research provided new methods for many problems in number theory. As an important tool in number theory, sieve methods are widely used in the study of the prime number theorem, Diophantine equations, and modular forms. Chen Jingrun's ideas about sieve methods influenced later mathematicians such as Ben Green and Terence Tao, who further developed these theories in sieve methods and analytic number theory. Chen Jingrun's work on modular forms and analytic number theory provided important insights for the development of modern number theory. As an important object in number theory, modular forms are widely used to study Diophantine equations, the relationship between modular forms and prime number distribution, and the application of modular forms in algebraic geometry. Chen Jingrun's ideas about modular forms influenced later mathematicians such as Robert Langlands and Ivan Vinogradov, who further developed these theories in the intersection of modular forms and number theory. Chen Jingrun's research on inequality problems provided a new perspective for understanding complex structures in number theory. The inequalities he proposed have wide applications in number theory research, especially when studying prime number distribution, congruences, and Diophantine equations. Inequalities have become an important tool for understanding number theory structures. Chen Jingrun's ideas about inequalities influenced later mathematicians such as Henryk Iwaniec and Fields medalist Maxim Kontsevich, who further developed these theories in inequalities and congruences in number theory. Chen Jingrun's mathematical research has wide applications in modern AI technology, especially in number theory, modular forms, sieve methods, and inequality problems. Here are some specific applications. Number theory and cryptography. Chen Jingrun's research on number theory has significantly impacted modern cryptography. Chen's theorem and sieve methods are widely used in cryptographic algorithms, especially in public key crypto systems. Chen Jingrun's ideas about number theory provide the mathematical foundation for developing secure crypto systems, ensuring the security of data during transmission. Modular forms and machine learning. Chen Jingrun's work on modular forms has profoundly impacted modern machine learning. Modular forms are used to study the symmetry and invariance of data and are widely used in deep learning, pattern recognition, and image processing. Chen Jingrun's ideas about modular forms provide the basis for developing efficient machine learning algorithms, enabling AI systems to process complex, high-dimensional data. sieve methods, and big data analysis. Chen Jingrun's research on sieve methods has significantly impacted modern big data analysis. As a method for data screening and filtering, sieve methods are widely used in big data analysis, data mining, and information retrieval. Chen Jingrun's ideas about sieve methods provide the basis for developing efficient big data analysis algorithms, enabling AI systems to extract valuable information from massive amounts of data. Inequality problems and optimization algorithms. Chen Jingrun's contributions to inequality problems have profoundly impacted modern optimization algorithms. Inequalities are used to solve optimization problems, such as parameter tuning in machine learning and gradient descent in deep learning. Chen Jingrun's ideas about inequalities provide the basis for developing efficient optimization algorithms, enabling AI systems to find optimal solutions in complex, high-dimensional spaces. Chen Jingrun's mathematical research not only promoted the development of modern number theory, but also promoted the development of modern AI technology through fields such as number theory, modular forms, sieve methods, and inequality problems. From cryptography to big data analysis, optimization algorithms, and machine learning, Chen Jingrun's ideas continue to play an important role in today's technological world.